Hello everyone, welcome to Sri Chaitanya Academy, and I also welcome you to this chemistry transition course where we are discussing about concepts that will be helpful to you in 11th. Now moving on to this session which talks about really something at the core of today's progress, that is quantum numbers, right? So what are these quantum numbers, how these quantum numbers came into existence? You might have heard about the term quantum computing, right? So all that quantum numbers, quantum computing, all that originates from this, yes, quantum numbers. So the word quantum means, if I talk about the word quantum, okay, this word means to put in packets. Okay, so first time this word quantum came into existence when you talked about Niels Bohr. Right? You have studied in your 10th class that what picture you have studied of an atom, that there is a nucleus, and around that nucleus in circular orbits electron is revolving, right? So there is electron here, and electron here revolving in orbits, right? And then these shells are called KLM, right? Now what Bohr told that electron can revolve in only those orbits where the angular momentum, yes, when you are moving in a straight line you have linear momentum. So if I talk about linear momentum, it is m into v, velocity, but I am talking about angular momentum, right? When I talk about angular momentum, it is mvr, right? So Bohr said that if suppose I am the nucleus and around me there are orbits and electrons are revolving, can electron revolve in all orbits? If that is the case, there will be a number of orbits here, right? Does the earth revolve, does the planet around the sun revolve in all the areas, all the orbit? No, right? It will be somewhere here, and then after that there is an empty space, and then here. So why there is no orbit in this empty space? It is because an electron can revolve only in those orbits where the electron's angular momentum is what? N h by 2 pi. H is the Planck's constant, right? This is your Planck's constant, right? And n, right? Focus your attention on n. What is n? N is a integer, a positive integer, where n can be 1, 2, 3 and 4. But n now cannot be a decimal. N cannot be 1.5. It cannot be 2.5. So it has to be whole numbers. So this means what? It means that the angular momentum has to be in packets, like 1 packet, 2 packet, 3 packet or 4 packet. Nothing half packet, right? So this complete packet is called quantum. Each packet is called a quantum, right? So this quantum means anything, angular momentum, energy. If you if you fill these properties, this energy, angular momentum, into packets, whenever you see a number which is a whole number, and besides that as constant, right? Pi is constant, h is Planck's constant, 2 is constant. So this is called the principle of quantization, right? And this n which was first told by Niels Bohr is the first quantum number. So n is your first quantum number, right? which is also called principal quantum number, right? Now, like n, there are some more quantum numbers. L, which is called the azimuthal quantum number, right? M, which is called the magnetic quantum number, and S, which is called the spin quantum number. Right? These are the 4 quantum numbers. Now, why? See, each quantum number, the mathematics is fairly complex for you to understand, but remember, each quantum number represents something, and that something is quantized, right? Right. So what values they can take, whatever, we'll go in detail. Now, from where does this quantum, the first quantum number, okay, Niels Bohr first time proposed it, right? But what about these quantum numbers? From where do they come? They come, all these quantum numbers, right? All these quantum numbers originate from a very special equation called the Schrodinger's equation, right? Schrodinger's equation, which looks somewhat like this. Right? And if you solve this equation, right, during solving these equations, to get the solutions, you, by mathematics itself, you are forced to introduce these quantum numbers. Okay, here till here, this does not come from Schrodinger's equation, right? Does not come from Schrodinger's equation, right? This one. But these 3, N, L, M, they come directly from the solutions of the Schrodinger equation. No need to go to detail of this, right? Right now, understand that, right? Now, what is the significance? So if I talk about the significance, right? If I give it a topic here, if I talk about the significance of quantum numbers, what do they represent? Well, understand that you live, as an example, to understand that you live in your house, right? So, you live in your house, right? This house has an address, right? This house has an address, correct? Now, how do you specify the address? Like 30 by 21 A, right? Like, so this is a address of Hyderabad, right? And then you have here Hyderabad, which is in the state of Telangana, right? So in this address you have some numbers here. A means the block, then this is your place inside Hyderabad, then you have Hyderabad, then you have Telangana, right? Like this N, L and M and S, all of them are parts of the address of what? What we are addressing? What is revolving in the orbit? Electron. So this N, L, M and S give us what? They give us the address of the electron. They give you the address of an electron. I cannot put it more simpler than this, right? It tells you the position of the electron and many more things we will learn. So now let us now focus on the first, the principal quantum number, right? Let us go to that in the next slide. So now I'm going to talk about the principal quantum number. There are some points related to that represented by small n. The first point, this was proposed by Niels Bohr, right? So Niels Bohr proposed this. Second, each n value, right, represents shell, right? Third, what does it give? It gives the size and energy, gives the size and energy of electron, right? Fourth, the number of electrons in a shell, if I talk about the number of electrons in a shell, is given as 2n square, right? Fifth, the angular momentum is given by n h by 2 pi, right? Sixth, you remember the K, L, M, N. This K, L, M, N, if I take the value in terms of n, is K will be 1, 2, 3 and 4, right? So this is your, and the picture which it represents is this, that you have a nucleus and around that nucleus you have your orbits, right? So here you have K, L and M, or you can say 1, 2 and 3. And remember it represents the shell. Now this picture you already know from what? From your 10th standard. But we are not in 10th, now we are going to go to 11th, right? So now this complete way of discussion is that I am using, imagine I'm using a microscope, right? Earlier you used to see this shell. Now with the microscope we will go more into details of these shells as if there is something else in this one shell also. What is that? It is the next quantum number called the azimuthal subsidiary, right? Quantum number represented by small l. So what does this quantum number represent? Let us talk about point by point. The first point. See one point in the previous slide also I forgot to add. Just write it down here, the 7th point. As, now I remember, as n, the value of n increases, energy also increases, right? So if there is an electron in one orbit, its energy will be less. As the value increases from 1 to 2, the energy of the electron will also increase. So what I am trying to say is that electron in the third shell will have a higher energy than electron in the first shell, right? So this also works like this. Now coming back to this. So shape also, right? In a way it is also telling the shape, sorry, the size. This is this much, the other one is little big, other one is little big. So n is telling you the size and energy, size and energy, remember. This on the other hand tells you what? Tells about the shape, right? Next, what does it represent? It represents subshells within a shell. Third. So subshell, yes, now I'm talking about subshell, right? So there was a shell, you moved in the microscope, checked, there are some more lines there. So these are called subshells, right? For each n value, we have what? We have n L values, right? We'll talk about that, right? For a n value, right, L ranges from 0 to n minus 1, and finally I talk about the angular momentum in subshell is given as L plus 1 h by 2pi, right? This is all about this shape. Right? How does it tell you shape? Now I told you, let us take an example. Let me take an example now, right? Focus on this point. For n value, L ranges from 0 to n minus 1. So let us take L value of, suppose let us take the L value of 0 first, 1. Remember, here I am putting the value of n, and L can range from 0 to n minus 1. So if the n value is suppose 1, then 0. N minus 1, 1 minus 1 is 0, so it can, L value can be only 0, right? This is the value of L. If n is 2, how many L values I can get? 0, I can start with 0, n minus 1, 2 minus 1 is 1. So I keep on writing from 0 numbers till I get 1. So I'll get 0 and 1. If the n value is 3, 3 minus 1, 2. So I have to write 0, 1 and 2. Similarly, if I have 4, I have to write 0, 1, 2 and 3. So these are the values of L. Now, if the value of L is S, then the subshell is called small s subshell. If the value of L is 1, the subshell is called small p. If the value of L is 2, the subshell is called small d. And if the value of L is 3, it is called the F subshell. Okay. Now, one more representation. This S subshell is of n equals to 1. So I can write this as 1s, where this represents the value of n. Similarly, this is also S, this is S, this is P, this is S, this is P, this is D. So I can write this also as, because the n value is 2, this will be 2S, this will be 2P. Similarly, you have 3S, 3P, 3D, and here you have 4S, 4P, 4D, and 4F. Right? So tell me, if n has a particular value, how many L's are you getting? If n is 2, how many L's you are getting? 1, 2. If L is 3, how many N's you are, if n is 3, how many L's you are getting? 1, 2, 3. So right, there are n values of L. Right? Now, right. Okay. So this next point, it talks about the shape. So how is the shape predicted? Well, L is equals to 0 or I have an S subshell. The shape is spherical. So it has a spherical shape, right? But when L value equals to 1 and the subshell is P, then it has a dumbbell shape. See, dumbbell means the dumbbells which we use, right? Remember, to build muscles, this is called a dumbbell, right? It has two, right, solid spherical parts. Same way it has two solid spherical parts, so it has a dumbbell shape. Right. Now, moving on to the next. L equals to 2, so the orbital is D. This is double dumbbell. Means, right, this is double dumbbell. Right. So in this way, based on the values of L, we can decide how the subshell will look. So that is L for you, right? Now another thing, okay, afterwards we will see, right? This is the shape, right? Let me see if all the points are covered. This is covered, this is covered, this is covered, this is covered, this is also covered. Now moving on to the next quantum number, which is your magnetic. Let me take another. Magnetic quantum number small m. Now, why this word magnetic? Why is this magnetic thing? Understand that if you do not have a magnet, right, then you will not be able to see the effect of this quantum number. Just write down the points first and then we will discuss. So, what does it do? It represents the orbital, right? It represents the 3D arrangement of orbitals in space, right? In space. Third, for each value of L, we have 2L plus 1 values of M, right? And fourth, for each L, M is equals to minus L, minus L, 0 to plus L, right? And in each subshell, orbitals in a subshell, How many orbitals in subshell? 2l plus 1. Right? It represents energies in presence of magnetic field. Right? Let us understand. Right? So it represents orbital. Right? It represents three-dimensional arrangement of orbitals in space. For each value of L, we have 2L plus 1 values of M for each L. Right? Let us get a feel of it. Now, for that, I'll refer back to this place. And let us change it a little bit. Right. Now, here I'm going to refer to the values of M. Right. So, M will be from minus L, 0 to plus L. Okay. So, 0 in itself will not do anything, right? So, 0 means 0, only 0. Here also it will be 0. Now, my L value is 1. I can go from minus 1, 0 to plus 1, right? Here also you will get 0. Here if I talk about, you will get minus 1, 0, plus 1. Here, see minus L. So, minus 2 you have to start. Then minus 1, then 0, then plus 1, then plus 2, right? Similarly, I can go with this L equals to 3, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, right? Now, some inferences we are going to get from this. What are those inferences? Now, each value of this M represents a orbital, right? So, we started from shell, we went to subshell, now from subshell we are going to orbital, right? Now, tell me in N equals to 3, how many orbitals are there? N equals to 3, let us count. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, right? So, it has a total of 9 orbitals. Can you sense a relation here? Yes, yo-yo 9. Now, what about this? N equals to 2. 1, 2, 3 and 4. So, total you are having here 4 orbitals. So, can you think of a relation between N value and number of orbitals in that N? You can see 2, 4, 3, 9. Yes, the clear relation is, if I talk about number of orbitals, okay, not here, it's very, what can you tell for number of orbitals? Please, if anyone is able to find the formula, it's right in front of you. Number of orbitals will be N square. N square, right? It will be N square, right? Like that way, for 3 it is 9. For 4 it will be 4 square, 16 orbitals, right? So, number of orbitals equals to N square. It is your next point. 7th. 8th point. Each orbital can keep maximum of 2 electrons, right? So, now each orbital can keep 2 electrons. So, what I can say, 9 total electrons in a shell will be twice of n square, right? And total electrons in a subshell, how many orbitals are present in a subshell? 2l plus 1, right? This l plus this l plus 0, so 2l plus 1, twice of that, right? So now coming to this point, it represents a 3D arrangement of orbitals in space. How is that? So 3D arrangement of orbitals in space. So how does that work? So let us take the example of L equals to 1, which is the p orbital. For that, the values of m are -1, 0, plus 1. So what do I mean by that? What I mean is, suppose you have 3 axes. Suppose this is your x-axis, right? Then this will be your y-axis, and this going in is your z-axis, right? If this is the way I drive all the axes. Now, p orbital is dumbbell shaped, right? So now I'm going to draw just the x-axis. Suppose this is the x-axis, this is the origin, right? This point. So the orbital which has, suppose this is the orbital called px, which with m equals to -1. This orbital will be like this, right? If I erase this and draw it more artistically, here and here, right? It is surrounding the x-axis. Similarly, if I talk about the y-axis, so here this is the origin, right? And this is your y-axis. This is called P. And finally, one more is there, right? This is your z. Let us draw that also. So your z axis. See, understand that these are 3 different arrangements of the p orbital in this space, right? Now, if I draw all of them together here, how will it look? Right? So, all 3 together are like this for L equals to 1. So, in L equals to 1, there are 3 spaces where electron can come, and in each space you can have 2 electrons, right? Right? So, this can have 2 electrons, this can have 2 electrons, and this can also have 2 electrons. So, 2 electrons can come in each of them, giving that P subshell can accommodate a total of 6 electrons. This you can also get from this formula, right? L is 1 plus 1 becomes 6, right? So why this 3-dimensional arrangement is required? Well, I'll tell you. In the absence of magnetic field, all orbitals of a subshell have equal energy. So what I'm trying to say is, if I have Px, Py, Pz, right? The last one was Pz, right? All of them will have same energy in the absence of magnetic field. Means if there is no magnet involved, they will have same energy. But as soon as you put a magnet, if I put a magnet north, south, magnetic field going from north to south, then the energy of these orbitals changes, and now suppose Px, Py and Pz. How it changes? Not for now, next discussion, but in the presence of magnetic fields, it splits. How visually you will see? Suppose, see, this was Bohr's picture, shell. Now, let me take a magnifying glass and look into this, suppose this shell, n equals to 2 shell. As I look into this shell, what I see? How many subshells? 1, 2, 3, 4. 4 subshells, right? Of L value as 0, right? And these are L value as 1. But in this, each of them, M value will be, suppose, no, this is your M value, 0, minus 1, 0, plus 1, right? So, even the subshell, this was the S subshell, this was the P. Now the P subshell, which was, you were believing that it is 1, it is also split into 3, and based on the distance from the nucleus, each of them will have different energies, right? More closer it is to the nucleus, higher will be the energy, right? And if I talk about the closeness, S, P, D, F, right? This is the closeness, right? Distance from the nucleus. Now remember that in each of them, P, D and F, there are subshells present. I have not drawn it because you can only see it by a, not actually a magnifying glass, but that is just a way of me telling you this, right? So the energy order of this is, S orbital has the lowest energy because I told you as n increases, right? So S, P, D, F. This is your energy order of orbitals or subshells, right? So understood? So these all are present like this. Their energies become different if you apply a magnetic field or magnet. In the absence of magnetic field, they all have the same energy. That is why when you discuss L, there we have not talked about the splitting of this L, because this we are discussing in the absence of magnetic field. Now you apply magnetic field, you'll get so much of quantum number thing here, right? N we have discussed, L we have discussed, M we have discussed. Now coming to the last quantum number, which is the spin quantum number. Represented by S. Now this is also represented by S. So to not have any confusion, somewhere it is written as small s, or they will also write it as ms. Now remember that this quantum number does not come directly from Schrodinger's equation, right? It comes from logic. So each electron can have only two values of S, that is plus half or minus half, and the spin only angular momentum is again S plus 1 under root h by 2 pi. Right. So what do I mean by spin quantum number? Understand that. Electron, consider that electron is a charged ball or particle, right? So this is the nucleus. This charged ball or particle, right, is moving around the nucleus in a circular orbit, right? Because it is moving around the nucleus circular orbit, due to this movement, it has what? It has angular momentum, right? It has angular momentum. But this ball, like Earth, remember Earth revolves around the sun, but Earth also spins on its axis. Do you remember Earth spins on its axis? That is the reason we are able to say that you will get day and night. If Earth was not spinning on its axis, you will not get day or night, right? So same way, an electron, this is an electron, right? Magnified electron. This also spins on an axis, right? If it spins in a clockwise fashion, then S value is plus half. Now if the same electron this is the axis, spins in a anti-clockwise fashion, S value will be minus half, right? And due to the charge spinning on the axis, what it will also have now? It will have what? Spin angular momentum, right? Which I already told is given by this particular formula, right? So these are the quantum numbers. Now let me give you a feel of these quantum numbers, right? Suppose, see, all of you are in school, right? So suppose this is a school building, right? In this school building, there are various floors, right? In each floor, there are benches, and on each bench, two students can sit. Yes, don't make me draw all of this. Right. So two students can sit. Right. So now carefully observe what I am saying. This building is same as an atom. Imagine this is an atom. The flows that you are having are what? Flows are shells. Right. The benches, in each floor there are benches. benches are equivalent to what? Subshells. Right? 1 minute. Let us take one more thing. So, one more thing I'll do, that there are classes also here, right? Suppose this is one class, this is the other class, right? These are class, right? One class, the other class, right? So on each floor there are classes, right? So each class is your subshell, which is L. Now, in one class, you have many benches, right? So, once again, let's rewind. You have a building, you have floors. Each floor has many classes. In each class, you have many benches, right? So, now I can say that benches are your orbitals, represented by M. And what are you sitting on the benches? You are, what are you sitting on the benches? The students are electrons, right? And these students are rotating somehow, right, sitting on the benches. Due to that rotating students, suppose they are rotating also, that rotation of those students is represented by, so now next I am talking about the rotation of students is represented by the spin of electrons, S. Right. So N, L, M and S, this you can clearly understand through this analogy, right? The building is the atom. In the atom you have various floors. In each floor you have various classes. In each class you have benches. On each bench two students, electrons can be there, and each student will rotate on its axis, giving you the spin. So this is the whole analogy and whole structure how an atom is built up, right? So in today's class we studied about quantum numbers, right? Numbers N, L, M, S. They give you the address of electron, right? And finally I will say this something calls, this is called NLM, right? This is called psi, right? And this is the symbol that represents an electron. We'll learn more about it, but for now these you have enough knowledge to understand these. So let me just quickly go to the last slide if it comes, right? So yeah, finally it came. So with this I end today's session on quantum numbers, which originate from Schrodinger's equation, and they start the concept from the Bohr's model of atom, which you have studied in 10th, right? So if you liked this session, if you like the conceptual clarity that you're getting in these things, then I will suggest you that quickly go here, fill this Google form so that we can know about you, right? And as a next step, join our Telegram channel to get regular updates, questions, practice sessions and PDF of this session also you will be getting on Telegram. So the next you have a math session, right? Stay tuned for that. But from my side, it's bye-bye, right? From quantum numbers and from